yj t. So expected value of e raised to it sigma yj, and if we simplify, this is product j running from 1 to n, expected value of e raised to it yj, because it is e raised to it y1 into e raised to it y2 and so on. Since all y's are independent, e raised to it yj's are also independent, and therefore expectation of their product is equal to product of their expectations. So this is nothing but product j running from 1 to n phi yj t. So this is equal to product e raised to it mu j minus lambda j into mod t, and so base is same, so powers will be added when we take multiplication. So e raised to it sigma mu j minus sigma lambda j into t, and as we know, this is the characteristic function of Cauchy distribution with parameters sigma mu j and sigma lambda j, and therefore by inversion theorem we can say that the distribution of sigma yj is also Cauchy with parameters sigma mu j and sigma lambda j. Now similarly, if x1, x2, xn are standard Cauchy, are independent standard Cauchy variates, then if you obtain the distribution of its mean 1 upon n sigma xj, say x bar. So if x1, x2, xn are independent standard Cauchy variates, then distribution of x bar is also standard Cauchy. That we can easily prove from this, because all mu j's are same and lambda j's are also same. Now suppose x is standard Cauchy variate, therefore its probability function is 1 upon pi into 1 upon 1 plus x square, ranges from minus infinity to infinity and 0 otherwise. Now I wish to obtain the distribution of x square. I call it y, say distribution of x square. So the distribution function of y is equal to x square is, say f y y is equal to probability that y is less than or equal to y. That means probability that x square is less than or equal to y, means probability that minus root y is less than or equal to x is less than or equal to root y. So to find the probability, we have to just integrate the standard density function of standard Cauchy, that is 1 upon pi 1 upon 1 plus x square dx over the range this minus root y to root y, and as you know, this is even function of x, and therefore we can write 2 times 1 upon pi integral from 0 to y 1 upon 1 plus x square dx. So this is equal to 2 upon pi, integral is tan inverse x 0 to root y. So 2 upon pi tan inverse root y minus tan inverse 0 means 0. So this is the distribution function of y is equal to x square. Now if we differentiate this with respect to y both sides, then we shall get PDF. So the PDF of y is equal to x square is, say gy is equal to derivative of fyy. So 2 upon pi is constant, derivative of tan inverse, that is 1 upon 1 plus y square of root y, and derivative of root y is 1 upon 2 root y. So 2 is cancelled. This is root pi into root pi. This is y raised to minus half 1 plus y. So this is gamma half, root pi means gamma half, 1 means I can write gamma 1, this is y raised to half minus 1, and 1 plus y raised to half plus half. Say, so this is 1 upon beta half half. Then y raised to half minus 1, 1 plus y raised to half half. So actually this is the PDF of beta type 2 distribution with parameters half and half. Of course we have to take this distribution afterwards. So if x is a standard Cauchy variate, then distribution of square of x is again beta type 2, and range of y will be from 0 to infinity. One other result, suppose x is normal 0 1, y is normal 0 1, x and y are independent. So we consider two independent standard normal variates. In last two sessions we have studied this normal distribution. Now I just wish to obtain the distribution of x upon y. Distribution of x upon y, I call it say u. So we want to derive the distribution of ratio of two independent standard normal variates. Now both are standard normal, so say PDF of x is 1 upon root 2 pi e raised to minus half x square. PDF of y, say I denoted by f2y, that is again 1 upon root 2 pi e raised to minus half y square. Here range of x and y both are from minus infinity to infinity. Since they are independent, their joint probability function is equal to product of their marginal probability functions, and therefore it is 1 upon 2 pi e raised to minus half x square plus y square. Range is from minus infinity to plus infinity. Now to obtain distribution of u, which is x upon y, just take transformation u is equal to x upon y and say v is equal to y. That is x is equal to uy means uv and y is equal to v. Here u and v both will be from minus infinity to infinity. Now if we find Jacobian, say j, that is dxy duv, this is Jacobian of the transformation, that is dx by du, dx by dv, in the determinant dy by du, dy by dv. So dx by du is v, dx by dv is u, dy by du 0, dy by dv is 1, so ultimately v. And therefore if we obtain the joint probability of u and v, guv is equal to 1 upon 2 pi integral, e raised to minus half x square means u square v square plus y square means v square and into mode of Jacobian, mode v. Here again u and v both are from minus infinity to infinity. Now if we want probability function of u, then we have to integrate this over v. So the marginal PDF of u is, say I write it g1u is equal to integral over v. V is from minus infinity to infinity, guv du dv is equal to 1 upon 2 pi integral guv means e raised to minus half v square common in the bracket u square plus 1 more v dv. Now this is even function of v. integral is over v, and therefore it becomes 2 times. So it becomes 1 upon pi 0 to infinity e raised to minus half v square u square plus 1 into mod v dv, but mod v is equal to v when we take range v as from 0 to infinity. Now to obtain this integral, you take say 1 upon 2 v square into u square plus 1 is equal to say w. If you integrate, then 2v dv, 2v into e square plus 1 is equal to dw. So this is equal to 1 upon pi 0 to infinity, and this is e raised to minus w, and v dv means dw into u square plus 1. So 1 upon pi, this is range of v. So as far as v is concerned, u square plus 1 is considered as constant, and therefore it can be taken out. Integral of e raised to minus w is minus e raised to minus w 0 to infinity. So when we put w is equal to infinity, e raised to minus infinity is 0, minus 0, minus minus plus, putting w is equal to 0, e raised to 0 is 1. So ultimately this is 1 upon u into 1 upon u square plus 1. Range of u is from minus infinity to infinity, 1 upon pi. So this way, which is the PDF of standard Cauchy. So this way, u is a ratio of two independent standard normal variates. So the distribution of ratio of two independent standard Cauchy variates is again standard Cauchy. So now I request Professor Chaudhary to discuss some Laplace distribution, Weibull distribution and their applications. Chaudhary sir.
So Weibull distribution is again a continuous distribution, and the definition is a continuous random variable capital X is said to have a Weibull distribution with parameters alpha and beta if the density function is given by this particular form: fx alpha beta equal to beta upon alpha into x upon alpha raised to beta minus 1 into e raised to minus x upon alpha raised to beta, where x is positive, alpha beta both are positive, and the density function is 0 otherwise. Now here in Weibull distribution there are two parameters, alpha and beta. So alpha is called the scale parameter and beta is called the shape parameter of the distribution. And in the original Weibull distribution, if we take beta equal to 1, then we get the corresponding distribution, that is exponential distribution. So exponential distribution is a particular case of Weibull distribution. Now let us find the distribution function of Weibull distribution. The cumulative density distribution function of Weibull distribution is, so this is the definition of distribution function, that is fx equal to probability x less or equal to x, that is probability integration over range 0 to x density function. Now in this integral, if we transform this x upon alpha raised to beta by y, then we have, if we differentiate this, then we get beta upon alpha into x upon alpha raised to beta minus 1 dx equal to dy, and from this transformation the reverse transformation is x equal to alpha into y raised to 1 upon beta, and using that in the previous formula, this particular formula, we get fx equal to integral over this range into e raised to minus y dy, and this is a standard integral, exponential integral. So integrating this and substituting this range, so we have the density function of fx is 1 minus e raised to minus x upon alpha raised to beta. Now the mean and variance of Weibull distribution. So mean of Weibull distribution is alpha into gamma 1 upon 1 plus beta, and the variance is mu 2, that is alpha square into gamma 1 plus 2 upon beta minus alpha square into gamma 1 plus 1 upon beta raised to 2. Now let us find the median of the distribution. So we know that median is the value which divide the whole distribution into two equal parts. So obviously from the distribution function one can easily determine the median of any distribution. So we have fx equal to 1 minus e raised to minus x upon alpha raised to beta. So let m be the median of the distribution. So we have fm equal to 1 half. So using, that means replacing x by m, we get the value of fm equal to 1 half, and after simplification we have the median is equal to m upon alpha, that is equal to log of 2 raised to 1 upon beta, or simply it is median equal to alpha into log of 2 raised to 1 upon beta. Now this is the graph of Weibull distribution. Now if you look at this here, there are two parameters. One is a scale parameter 2.5, other is a shape parameter 1.5. So the graph of Weibull distribution looks like this, and these are various parameter combinations for Weibull distribution. So this is for 1 1, this is for 3.5 and 2, this is for 15 and 6.5, this is for 5.5 and 6.5, and this is for 10 and 10.5. So this is about the Weibull distribution. Now let us discuss one example of Weibull distribution. Now in this case we have the life of a computer processing unit in hours is modeled by a Weibull distribution with parameters beta equal to 2 and alpha equal to 900 hours, and we want to find mean life of computer processing unit, variance of the life of computer processing unit, and the probability that the CPU fails before 500 hours. So let us denote this x. X is a random variable which is Weibull random variable, and it denotes the life in hours of a computer processing unit. So x follows Weibull distribution with alpha equal to 900 and beta equal to 2, and we know the mean of Weibull distribution. So using that formula and putting the value of alpha and beta, we get mean equal to, this is very simple arithmetic. So after simplification we get it is 797.7645 hours. So this is the average life of that computer processing unit. Now let us find the variance. So again we know this formula, and we know the value of alpha is 900 and beta equal to 2. So again after simplification we get the variance of that x is this number, and now let us find the probability. So we know the distribution function of Weibull distribution. So using that distribution function one can easily determine the probability of this type of event, that is probability x less than 500. We want to find probability that CPU fails before 500 hours. That means probability that x, because x is the life of CPU, life in hours of CPU, so probability that x is less than 500. So it is simply using this particular definition